Hello everybody, we continue, and let me recall, we consider a curve in R3 and we constructed three vectors which are related to the curve. So unit tangent vector, unit normal, and orthogonal to them is binormal. As far as I remember, I finished on the definition of torsion, right? Am I right? Sorry? Yeah, tau, yeah, torsion, yeah. Torsion was defined. So we finished on the definition of torsion, which is just tau times n, unit normal. Okay, so torsion was defined, and also let me recall that dt over ds is kappa times n. It was in the definition of the curvature. So curvature and torsion. Those quantities are very important, and I would like to spend some time to clarify their meaning, also to discuss in more details planes which appear here. Let me recall which planes we have. Osculating plane generated by T and normal plane orthogonal to n, so it means generated by BT, and also rectifying plane so the rest generated by B and M. So for the sake of convenience, what happens with chat? I cannot see questions.
Yeah, there is no question right now. They are coming to fix it.
Okay. So let us try to understand what are equations for those planes. So the easiest is normal plane equations for those planes. And denote by rho a vector on the plane. So I'll give equations in vector form. Rho is a vector which runs along the plane. So, what are equations? For normal plane, it's very easy, because, as we know, normal plane is orthogonal to the unit normal vector. And unit normal vector was computed just as or maybe easiest way, maybe I'll start with the rectifying. It is even easier. Yeah, I'll start with rectifying, sorry, it's simpler. So rectifying, because look, rectifying plane is generated by B and N, but it is orthogonal to tangent vector. Orthogonal to tangent vector means that when we consider a vector, rho is a radius vector of a point on the plane. Radius vector of a point on the plane. So, for example, for rectifying plane, you see we have an origin somewhere, right? So, if I consider a point in our plane, then rho is vector to that point, rho. And let it be point R at T naught. That is a point on our curve, which belongs to our curve. Then the vector, that one, this difference, is a vector which belongs to our plane. So, because difference of two vectors belongs to the plane, right? Look, so rho is a vector from the origin. R is also from the origin to that point. I don't want to make extra drawings. And you see, difference is a vector which belongs to our plane, right? So, rectifying plane, as we know, this vector is orthogonal. So, rho minus R at T naught is orthogonal to the tangent plane. So, it means orthogonal to derivative. Okay. That is rectifying plane. What I wrote? Oh my God. What I am doing? I am very sorry. What I am doing? No. Rectifying and normal. Normal is orthogonal to the curve. Normal to the curve, of course. Yeah, so that is normal, as I said, the easiest. The easiest is normal, of course. Yeah. And last time I gave the definition like that, of course. Normal plane is orthogonal to our curve. So it is orthogonal to the unit tangent vector. That is generated, plane generated by B and N is normal plane, and the vector is orthogonal to our curve. Okay, so next plane, let us think about osculating plane. Osculating plane. It is generated by tangent vector and normal vector. So normal vector, you see, it's written here. And how it is related to derivative with respect to arbitrary parameter. That is dt over dt over ds over dt. And this vector, recall also t, normal vector, is r prime of t over the length of r prime for an arbitrary parameterization. So, you see that the plane which is generated by n and t is the same as the plane generated by vectors r prime and r double prime. Why? Because, look, if you differentiate with respect to t, you differentiate this expression, this fraction, right? So, look, when we differentiate this ratio, what happens? As a derivative of ratio, how it will be computed? You differentiate numerator, right? Multiply by some constant. So that is a vector which is parallel to second derivative, right? Also, you differentiate that one and multiply by numerator. It will be a vector generated by r prime, right? So derivative dt over d capital T over dt is a vector which is a combination of r prime and r double prime. Also, the vector t is parallel to r prime. So the plane which is generated by t and n is the same as the plane generated by those two vectors. Okay? So it means that for rectifying plane, we can write the equation like that. So we have three vectors in one plane. Three vectors. Which vectors? First derivative, second derivative, and that difference. If we have three vectors in one plane, then, oops, I forget to write here equals to 0, otherwise it is not an equation, right? Yeah. And if you have three vectors in one plane, then remember from geometry how you may write the condition for three vectors to be in one plane. Triple product is 0, right? So that is precisely what I want to write now. Equals to 0. Equals to 0. That is for rectifying plane. Now, most complicated is, of course, yeah, not rectifying. What is going on with me? I don't understand. Osculating generated by t and n. And I'm talking about t and n, and what is it? I don't know. I don't know. What happens? Of course, this is about osculating. Oof. I'm very sorry. I don't understand what happens today. I'm talking about plane generated by t and n. I discuss this And it is written here, osculating plane generated by T and N, and I don't understand. That is osculating plane. Yeah. And the most complicated is rectifying plane. Now we need to find two vectors in our plane. We know two vectors, binormal and tangent. Tangent is the same as to put R prime. But for binormal, we can choose, you see, binormal is orthogonal to osculating plane, right? Binormal is orthogonal to both vector n and t, right? If it's orthogonal to n and t, then it's orthogonal to r prime and r double prime. Orthogonal to those two vectors, which vector is orthogonal to both of them? Vector product, right? Vector product is orthogonal to both of them. So, in the direction of binormal, we can choose vector product of those two vectors. It's the same direction, I mean, also orthogonal to the same osculating plane. Okay, so now we have three vectors once again, and we can write rectifying plane. So three vectors are, once again, this is for sure in our plane, also r prime, and vector product r prime times r double prime. And that is equals to 0. Right? That is the equation for the rectifying plane. So these are three planes which are connected to a curve, Okay, also we have very nice equations, right? But to go further, we need to understand what is this torsion. To compute, how to compute this torsion. So let us find an expression for torsion. And okay, computation of torsion. Computation of the torsion. What is it? Look, how may compute this torsion? If we look at this expression, then we can write tor equals to minus scalar product dB over ds times n. Why? Because if you substitute, right, n is a vector of the unit length, minus tor times n, minus cancelled, tor remains. So that is how to compute. Okay, then remember how binormal was defined. Binormal was defined as vector product T n. That was the definition of the binormal. So if we substitute, then what we have? Minus, so vector product. How to differentiate vector product? We know how to differentiate vector product. It means firstly we differentiate T s times n and then we differentiate n. Okay. Now, remember, yeah, dt over ds is parallel to n. Hence, this vector product is equal to 0, right? That is 0. That is 0. So what remains is that one, and I can recall, what is it? Vector products, and this is scalar product. That is triple product, right? Remember, what is triple product? Scalar product of a vector product times another vector. Did you study triple products? I use a lot of geometry, you see. So that is triple product. Roughly speaking, I may forget about those brackets, right? And then we have properties of triple products. If we change the order, minus appears. So I'll change the order, minus disappears. That is T n dn over dx. Now, let us remember what we have then. Okay. Firstly, let me write in terms of the arc length parameter. So remember, for arbitrary curve, we have two kinds of parameters. One is arc length parameter, which was denoted by S here. That is the most natural parameter for many formulas. And another, it's what we have in reality if we consider this curve as a trajectory of a point, time, t. So a parameter which is given. So firstly, I want to write down this expression in terms of the arc length parameter. Then this is dr over ds. That was definition of the tangent vector. Next is n. Okay, n. Let me recall one more formula. No. It's here. Yeah, it's here, you see. T is dr over ds, right? So n is what? Second derivative of r over ds twice divided by kappa. 1 over kappa times second derivative over ds twice. That is n, right? Now we differentiate this vector n with respect to parameter s. How we differentiate this expression? We should differentiate the product. So firstly we differentiate this. But if we differentiate this, then what happens? Look. So d over ds, 1 over kappa times d2r over ds twice. What is it? This, I can differentiate firstly this 1 over kappa, d2r over ds twice plus 1 over kappa times d3 r over ds thrice, right? And look. So I should substitute this expression onto the third place. But look, d2r over ds twice. If I put it here as a third vector, then what happens? We have the same vector on the second place and on the third place, right? Then triple product is 0. So we may forget about it when we compute this triple product, right? What remains is that one. So 1 over kappa times d3r over ds thrice. I can forget that is a constant, right? Not constant, scalar, right? Scalar may be taken outside of the triple product. So we have 1 over kappa squared times such a triple product. First derivative, then second derivative, and then third derivative. So you see, very nice expression, right? For the torsion, right? Triple product with 3 derivatives. Okay, now let's try to understand what happens if we'll compute it in terms of arbitrary parameterization, because arc length parameterization we need to compute. Then what happens? Okay, dr over ds, yeah, you see, the relation is always like that. You see, derivative with respect to s of a vector is equal to derivative with respect to t divided by ds over dt, or that is r prime of t. Recall, ds over dt is length of r prime of t, which is here. That was in the theorem about arc length of curve, right? Then, so what happens? Look, dr over ds, I should write like that: 1 over r prime of t, and here I have r prime of t. That is for the first derivative, right? Then what happens with second derivative? For second derivative, once again, I use the same trick. So we have an expression like that, right? And then we differentiate it with respect to t. Once again, we differentiate a ratio. Firstly, we differentiate this coefficient times that vector, and it means if we differentiate this and put it onto second place, what is triple product? 0. So it means that in fact I may forget about differentiation of denominator. I need to differentiate only numerator. So look, dr over ds is written here, right? I should differentiate it with respect to s one more time. One more time. One more coefficient like that appears, right? One more coefficient. And second derivative. Okay? Then that is what is written here, right? After that, I should differentiate one time more, right? I differentiate one time more with respect to s. Extra term like that appears, So altogether I have r prime of t cube and third derivative with respect to t. But these are scalars, right? So all of them may be taken outside of the triple product. That is 1 over, okay, 1 over kappa squared times r prime of t power 6. And then we multiply, okay, I may put here r prime of t, r double prime, and r triple prime. Last step is to use last theorem about computation of curvature. There was a formula for curvature. Let me recall it. Curvature was written as length of vector product r prime times r double prime divided by cube of, right? Now, if we substitute, look, kappa squared r prime power 6 appears, cancels. Those power 6 are cancelled, and what remains is that one, r prime of t, r double prime of t, r triple prime at t over square of vector product r prime of t, r double prime at t squared. That is a formula for the torsion. That is the formula for the torsion. Of course, it's rather complicated, but nevertheless, you see, it's a little bit easier than when you will try to write down in coordinates. I'll not do it to write down in coordinates. Okay, then one more thing. Look, I wrote two equations. So what we computed, derivative of binomial with respect to s, derivative of tangent with respect to s. What remains? Let's have a look at derivative of normal. Yeah. So let us compute derivative of the normal vector with respect to s. Okay, that is look, it was a vector n was here, right? Also over there. Maybe, look, for sure, this vector, we know there was a lemma that if we have a vector function of length 1, then vector of derivative is orthogonal to this function. That was a theorem, right? A of t equals to 1, then derivative is orthogonal to A. There was a lemma last time. Or maybe not last, before last. I don't remember. Yeah, I think before last. It was lemma at the end of lecture. Oh, number, no idea about number this lecture. of this section at least. It was in this section for sure. So then, as we know, this vector is orthogonal to n. Hence, if it is orthogonal to n, then it belongs to which plane is orthogonal to normal plane? Rectifying plane. So this derivative belongs to the rectifying plane, hence it can be written as a combination, linear combination of generating vectors. Let's compute what are coefficients. Coefficients alpha 1 dot product dn over ds times t. Okay, what was n? N was, yeah, that was derivative with respect to s of 1 over kappa times dt over ds, right? That is written over there, times t. So if we differentiate this multiplier, 1 over kappa, then what happens? If we differentiate that, then here we have derivative of t, scalar product with t. Again, by this lemma, it's 0, because we have unit tangent vector. So 1 over kappa may be taken outside, and we have then second derivative of t with respect to s, times t. Okay, and of course this was a very bad idea, because this way is very long, very long, very long. So we'll use different idea, and it will give essentially faster way. So look, the unit normal is orthogonal to b and t, and it has unit length. Hence, we can write this as vector product b times t. That is essentially faster. And after that, we differentiate vector product. That is db over ds times t plus b times dt over ds. Okay, db over ds is written here. So I can write minus 4 times n t plus, and here dt over ds, kappa n. So plus kappa times b n. Now, nt, look, b was defined as t times n. So nt, what is it? Minus b, yeah. So I'll obtain tor b. Then what is bn? b times n. Once again, that is not t, but minus t, right? Because it's in the wrong way. So minus kappa t. So we have three equations which are called Frenet or Frenet-Serre Theorem equations. Equations. And very nice way to write them down is to use matrix form. So if I'll use T and B, right? T and B. The order is T and B. And here T and B. Then what is it? dt over ds, look, kappa times n. So 0, kappa, 0. This is equal to that times that. dB over ds minus tau n, so 0 minus tau 0. dn over ds, tau time, minus kappa here, 0, tau. So these are necessary equations in matrix form. The matrix form. And also those equations, you started to consider differential equations. Did you start to consider systems of linear differential equations? No, not yet. But very soon you will consider them. And that is a typical example of a system of a linear differential equations. If you know functions tau and kappa, so if you know torsion and curvature, then you may reconstruct all parameters using the solution of this system of equations. So torsion and curvature determine completely the curve according to the theory of linear differential equations. So linear differential equations give you the solution how to find the curve if you know curvature and torsion at arbitrary moment. Also, I would like to finish to consider this topic with curvature and torsion by looking at physical. That will be lemma. Which lemma? 3, I guess. So there were 2 lemmas at the end of lecture. Which? 3 or 4? 4? 4? Yeah, 4. Lemma form. Lemma form. Sorry? Lemma 5. Okay. Let it be 5. Yeah. Lemma 5. Physical meaning, physical sense of curvature and torsion. Curvature and torsion of a curve with thrice differentiable R of t and such that what I need to exclude. I think nothing. I should. Oh, no. It's like that. Yeah. I think how I wrote, I forget what I supposed. Oh, I didn't suppose anything. I didn't write anything. Nothing about it. Nothing about such. Are angular velocities of the vectors of the unit tangent and of the binomial. Relatively. So you see, curvature, angular velocity of the unit tangent, and torsion, angular velocity of the binomial. And roughly speaking, what measures curvature? Curvature measures how the movement along a curve varies from a movement along straight line. So curvature measures how we deviate from a straight line movement. Yeah? And torsion measures how we deviate from a plane movement. So when we go along a curve, how we deviate from a movement in a plane. Right? So osculating plane is, roughly speaking, is a plane where our movement is at the moment. Right? And if we continue our movement not in this plane, then what it means? It means that osculating plane varies. And how to measure rotation? Rotation of osculating plane, it's the same as rotation of binomial, because binomial is orthogonal to osculating plane. So when you rotate osculating plane, it's the same as to rotate binomial. So you see that curvature and torsion, they measure angular velocities of those rotations. So you see, when a point moves in a space, then simultaneously everything varies. I mean, you go not along a straight line, but somehow in a curvilinear direction. Also, you go not in a plane. Also, you go in the space, right? You move in the space. So proof. For the proof, in fact, consider a vector function a of t of the unit length. Then let's compute what is derivative with respect to t a of t at a point, let's say, t naught. That is limit as delta t tends to 0, a of t naught plus delta t minus a of t naught over delta t, or shorter limit as delta t tends to 0, delta a of t over delta t. Okay, now let me draw a picture. Look, so if that is, let's say, a at t naught, that is a t naught plus delta t, then this vector is nothing else but the increment of our vector function at t naught. Sorry. Okay. Now, what is angle? How it is related to the angle between them? Angle phi. Let me compute the length of this, right? Then what is the length of this vector? Let's say unit length, right? So length is 1. Here length is 1. So what is the length of this? We have equilateral triangle, right? So if I put like that, then what is it? 1 times sine of phi over 2, right? That is half of our. So altogether we have limit as delta t tends to 0 to sine, okay, let it be delta phi, variation of the angle, delta phi over 2 over delta t, and also I should put modulo, of course. But as we know, if delta phi tends to 0, then sine tends to what? Sine tends to 0, of course, but sine is equivalent to its argument, right? Hence, we may forget about sine. Then we cancel 2, and it gives limit delta phi over delta t. And that is nothing else but angular velocity. Because what is angular velocity? You look at velocity of the angle. So delta phi is an increment of an angle, right? And now we apply, remember what is curvature, look. Curvature is the length of this derivative, right? So, as we know, length of derivative of a vector function of unit length is angular velocity of this vector. So we have angular velocity. Analogously here, torsion in module of torsion is equal to length of this, right? Hence, length of derivative. Yeah, so better to say, and here better to say modulo of torsion. Not the torsion itself, but modulus of torsion. Modulus of torsion. Okay, that's all for three-dimensional curves. What I wanted to say to you about. Now we consider plane curves. So from now on, plane curves will be considered. Yeah, okay, let it be here. N equals to 2. If n equals to 2, then for sure, what happens? Binomial doesn't change, right? The movement is in one plane. We have plane curve. So it means torsion is 0. And what are Frenet equations? Frenet equations. So dt over ds equals to kappa n, and also what remains? The last is nothing, but the second is still has a meaning. Which meaning? dn over ds is minus kappa t. So these are Frenet equations, Frenet series equations for a plane curve, And in fact, it has very nice meaning, those equations. So let me give a definition. Evolute of a curve is the locus of centers of curvature. Of the curve. Of a curve, let's say gamma, of the curve gamma. The curve, the original curve, gamma, is called an involute or evolvent. Different words are used. Involute of its evolute. So we have a curve. We may construct evolute. And for an evolute, the original curve is an involute. And now, theorem, number theorem. Which number theorem? Which? 5. Okay. Theorem 5. So suppositions. Now, let me recall. Yeah, here I should suppose. Suppose gamma is thrice differentiable. And such that dr over ds is never 0. Then an arbitrary tangent to the evolute of gamma is a normal to gamma. Moreover, variation of the radius of curvature of gamma is equal to the length of the corresponding arc of the evolute. evolute. Once again, I recommend you to look in Wikipedia for nice pictures of evolute and evolvent with, which also shows how normals are placed, how they vary, and so on. Okay, so proof. 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 Denote by rho of S a radius vector of a point on the involute. Oh, sorry, evolute. On the evolute. And let me recall how to compute center. We need to find, look, the definition. Evolute, to find evolute, we need to find where is center of curvature. Center of curvature, where is it? So at arbitrary point, it means that I need to take a point on our curve, R of S, and to shift to the quantity of radius of curvature in the direction of n. Of course, everything depends on S. So n of S. It's by definition. So where is center of curvature? We need to, so if we have a curve, now we have a plane curve, right? Then look, we think about the best approximation up to second order quantities by a circle, right? By a circle. And then center of this circle is precisely our center of curvature. So here we have R, and the vector is n, unit normal vector. So somewhere we have origin, that is R, and center of curvature is a point of our evolute, that is rho. Of course, the best way is to choose S to be arc length parameter for gamma, for the original curve. So we choose S as the arc length parameter for gamma. Okay, now let us compute. What is it? Maybe not yet to come. Sorry? Okay. Is it possible that in any case the circle intersect the curve? The circle intersects the curve. It touches the curve, in fact, you see. But in principle, it may intersect, doesn't matter. It's not a problem. No, not at all, yeah. Not at all. It may intersect, yeah. Why not? Not a problem. As I said, it's just the best approximation, nothing else. It may be in arbitrary. But I think it should not intersect. It should not intersect. Self-intersected. Maybe. I'm not sure. I'm not sure if it may intersect. At the moment, I cannot. Okay. Now, let's return to our theorem. So, what is Rho prime? Let's differentiate. That is R prime plus R prime times n plus R of s times n prime. Yeah? If intersects, does it mean something? Once again, no idea. At the moment, I am not ready to answer this question. I should think carefully. I doubt very much if it intersects. But I'm not sure. Really, I'm not sure. Really, I'm not sure. Okay. Then look. R prime is precisely, look, what is R prime? R prime of S, it should be somewhere dr over ds. Yeah, that is precisely, by definition, that is T, right? That is T. And then what is it? N prime is minus kappa T, so we have R times minus kappa T. And what is kappa? Is 1 over R. So we have minus T, it means they are cancelled. And what it means, look, Rho prime is derivative with respect to a parameter, right? When S varies, Rho varies along the evolute, right? So Rho prime indicates the direction of the tangent to the evolute. So Rho prime indicates direction along the tangent to the evolute, right? And what it says, this is the same as the normal, right? So tangent coincides with the normal to the original curve. N is normal to the original curve. So the first assertion is proved, right? And also look, if we want to compute the length of a evolute, then what we need to do? We need to compute the length of this, right? And to integrate it. Take the length and integrate, right? Then look, the length of in the right hand side, what is the length? Precisely R prime. If you integrate R prime, integrate from S1 up to S2 R prime of S ds, what you obtain? Difference of R, right? So in the left hand side we have difference of radii of curvature, right? In the right hand side we have a length of an arc of the evolute. So theorem is proved. I have 5 minutes. Yeah, and maybe very nice description of how to find the involute. So suppose we have a curve which is the evolute, right? Then how to reconstruct our curve from the evolute? So what is the involute? So the involute is the locus of a point of a taut string. So on a piece, a point on a piece of a taut string unwrapped from or wrapped onto the given evolute. So roughly speaking, imagine you have your evolute, right? Somewhere here. Okay, where is it? I think it's somewhere like that, right? So you have a string. Yeah. Piece of a taut string. Taut string. So taut string. Yeah, you have a string which is not a. My English is not sufficient. So you see, you have a string, right? Then what you do? You take this string and unwrapped it from a curve, and that is taut string. So every time it should be very straight, right? And when you do it like that, then this point is precisely the involute. An involute. In fact, not the an involute, better to say an involute, because there are infinitely many involutes, of course, right? Because you may start from arbitrary place of a curve. I recommend you to go to Wikipedia. There are very nice examples how to find, and there are movies even, right? Those things which are related to evolute and involute. Okay, so I wanted to give equations for the evolute, but I have only a couple minutes. That is really crazy. I'm not able to finish it in 2 minutes, and what I can do in that time. What I can do in that time? Okay, maybe I can start a little bit, but I want to recall an equation in the definition of, not in the definition, in the proof of theorem about computation of curvature. So during computation of curvature there was a formula. Let me recall that formula and I'll stop it to start next lecture with that formula. So d2r over ds twice equals to 1 over r prime of t squared r double prime of t minus 1 over r prime of t squared d over ds of the length r prime of t r prime of t. So this formula was contained in the proof of the theorem about computation of curvature. Later, this term was not interested for us because of, it was orthogonal to that, and that is why we could forget about it. But now I'll need to compute that one. Okay, that's all for today.